All right, go ahead.
All right. So good afternoon, good evening, good morning, wherever in the world you may be. Really glad that you can join us today. My name is Osinachi Ajoku. And as you can tell by my name, I'm Nigerian. And right now I'm currently an assistant professor at Howard University. And today I'll be talking about a topic that's somewhat different than the large scale scope of this entire summer school. I know we've been focusing mainly on the ocean, if not completely on the ocean, but I'm here to give a slightly somewhat different perspective. So the title of my talk today will be Biomass Burning, Aerosols, Precipitation, and Land Cover Interactions. And yes, the talk that I will give today is exactly as the title is presented. So just keep that in mind. So just to start off, a little bit about me. I'm currently an assistant professor, like I said, I'm 33 years old. I've been through the typical academic grind, as we call it, over here in the US. And I've been really fortunate to receive quite a few fellowships. Um, Sorry, I'm hearing the echo. Okay, I think that's taken care of.
Sorry
Yeah,
about that. I'm trying to mute.
no, it's okay.
Please continue.
So during my time, during my time in academia, I was really fortunate to get quite a few fellowships. So if anyone here is interested in going to grad school and figuring out how to self-fund your way through grad school, definitely take my information down. I was lucky to go through my PhD with fully funded fellowships, and I listed some of them here. After my PhD, I was even more fortunate to get something called an ASP postdoctoral fellowship, which stands for the Advanced Studies Program, which is a postdoctoral fellowship at the National Center of Atmospheric Research, which is a pretty big agency, for lack of a better word, when it comes in terms of atmospheric research globally. Currently, my endeavors include studying the impacts of black carbon or biomass burning on the West African monsoon, or what we call the WAM, connecting inner city communities with climate change, and advancing diversity, equity, and inclusion in academia. Some of my personal goals are something called science diplomacy. Most people don't really hear about that topic. When you think about academia, you really just hear about being a professor or a teacher. But there's something called a science diplomat, and I will just leave that there. If you're interested, keep that question down and ask that towards the end. I wanted to become a research professor, which I currently am, so that goal has been done. And of course, like many other people here, I'd like to take over the world one day. You could definitely ask me questions on that later. So as far as my research interest, the areas I conduct research in mainly focuses on aerosol cloud interactions. And in case you're wondering, well, OC, what the hell is an aerosol? Stay tuned, actually, we'll get there. So my research mainly focuses on something or a phenomenon called aerosol cloud interactions. And to study these interactions, I use both satellite observations and global climate modeling. And within that modeling, I listed some of the more specifications if anyone's interested. One of them being a refined resolution. So just in case you're wondering, what do you mean by refined resolution? Most models are created on a coarse domain. What we call coarse is really relative to what exactly you're studying. So most models are on 1 degree resolution, which is 111 kilometers by 111 kilometers. And as you can imagine, if you're trying to study something local scale, let's say at the village scale, I'm from Owerri. So let's say if I went to study something going on in Owerri, I'd need a much finer resolution, but I slightly digress. I'm also interested in aerosols and large-scale climate dynamics as a whole, air quality impacts from aerosol outbreaks, and to connect my research together with summer school at hand, I'm also really interested in oceanic atmospheric interactions. And in case you're wondering, well, what's an example of that? Stay tuned. I will actually go over that as well. So I didn't just want this to be, here's my research, here's what I do, if you're interested, talk to me kind of talk. I wanted to talk people through exactly how I conduct research. So this is my personal research methodology whenever it comes to any any kind of topic, whether it's new, whether I'm revisiting a past topic that previous scientists may have overseen something. I usually start off by, finding this interesting or unique question to solve using satellite or observational data. To me, it's very important that whatever problem you're trying to solve, you're actually able to see it first. And when we say see it, I'm not in the lab per se. Most of my work is done behind a computer screen. So for me to actually see something, I reference that to a satellite observation or using in situ observations from another previous campaign. Once we have those observations using satellites or some type of once we have that data from observations or some type of satellite, we want to quantify the robustness of the research results, depending on the type of research question we wanted to ask. So by doing this, we're able to explain the underlying mechanisms through observations. And then after using observations, it's important to deploy modeling techniques to decipher alternative hypothesis, or to explain the unseen and to take research to the next level. Most of the time when you're using satellite observations, you're limited to either the resolution or the time or the temporal scale of the measurements. So in order to go to the next level, as I would say, it's important to deploy specific modeling techniques tailored to whatever research questions that you're trying to answer. So what are aerosols? Atmospheric aerosols are just suspensions of liquid, solid, or mixed particles with highly variable chemical composition and size distribution. And that's exactly what you're seeing in this figure here. So aerosols, like I said, are liquid, solid, or mixed particles suspended in the atmosphere. So if you look at this image on the right, on the bottom, you can see that aerosols come from natural and anthropogenic sources. And this figure is just showing a slew of examples of aerosols as they are seen in nature, whether it's a massive dust storm, whether it's soot being emitted from the top of an exhaust from a truck, from the diesel combustion, whether it's biomass burning from outdoor cooking stoves, whether it's aerosols from large wildfires, or even aerosols created from waves crashing together. Aerosols have different sizes and chemical compositions. So these aerosols can directly impact planetary energy through absorption and scattering of incoming radiation. And aerosols indirectly impact climate by acting as what we call CCN, or cloud condensation nuclei. And when aerosols act as cloud condensation nuclei, they're able to influence the size of a cloud droplet and the resulting precipitation rates. And this is what's termed as the aerosol indirect effect. So just to go over one more time, aerosols can either directly impact radiation, or they can indirectly impact radiation. And more on this later. Of echo. So yeah, burning products and ash plays a sustainable role in Sweden agriculture. In the tropics alone, 50% of all aerosol emissions originate from anthropogenic fires. And this is something that I can assume that's more close to home for us, right? During the dry season, we tend to burn, things, whether it's for agricultural reasons, whether we're cooking using outdoor cooking stoves, like this image on the top left. It's kind of just been like an age-old thing to, burn wood outside for a numerous amount of things. But what's not really understood, or what hasn't been talked about until recently, and when I mean recently is more so the last 30 years, are the human health impacts associated with this burning. So in Nigeria alone, and this number is probably outdated, I'm pretty sure it is outdated, I remember it off the top of my head. According to the World Health Organization, there's about 95,000 deaths a year just from the inhalation of smoke from outdoor cooking. So that's something to keep in mind as well. So when you see a large natural fire like this, most of the time people are just thinking, it's just smoke, but there's actually a slew of chemicals that are emitted from this biomass burning combustion. And some of these chemicals are listed here. We have carbon monoxide, we have SO4, which is known as sulfate aerosols, which is a byproduct of sulfur dioxide undergoing extra oxidation. We have black carbon and organic carbon as well. So there's quite a few chemicals that are emitted from these large scale wildfires. Now, earlier I mentioned, aerosols have a direct effect and an indirect effect. I actually think it's pretty important to edge that into your mind, exactly what these direct and indirect effects are. So normally, right, let's say we have an ultra clean sky, right, which is super rare. There aren't really aerosols. This is what the atmosphere will look like, right? You just have incoming radiation, reaching the ground unobscured by any type of particles in the atmosphere, right? So under clear sky conditions, this is just meant to reflect what's occurring in the atmosphere. But this isn't always what's going on, right? So looking towards the African continent from the Atlantic Ocean, looking eastwards, right? We have the Sahel or the Sahara Desert to the north, and we have Southern Africa to the south. And depending on the time of the year, you have dust emissions coming from the Sahel, and we have biomass burning emissions or biomass burning aerosols coming from South Africa. So now let's introduce some aerosols. But don't forget, these are two different types of aerosols, one of them being dust and another one being black carbon. Now, when biomass burning occurs and these black carbon aerosols are emitted, they tend to be absorbing in nature. And I tried to create these arrows here to illustrate the absorbing nature of these black carbon aerosols. So imagine that the length and the width of these arrows is the intensity of shortwave radiation coming from the sun reaching you on the ground. When you have these aerosols lofted in the atmosphere, it actually absorbs this shortwave radiation, thereby decreasing the amount of intensity reaching the ground. You can think of a cloud, right? When you're outside and a cloud blocks your path between the sun and you feel a little bit cooler, right? Because there's less radiation reaching the ground. And essentially, that's what these aerosols are doing when they're lofted in the atmosphere, specifically absorbing aerosols. So on the other hand, let's say we have dust aerosols. Some dust aerosols are reflecting in nature or scattering. So they don't really absorb shortwave radiation as efficient as black carbon. So this leads to more scattering. So at the end of the day, this still leads to less radiation reaching the ground, but in this sense, in the sense with the dust aerosols, you have more radiation being reflected back into space. So regardless of both of these scenarios, we have a cooling of the surface and a warming of the atmosphere because these aerosols act to reduce the amount of radiation reaching the ground. And in both cases, it acts to warm the atmosphere as these black carbon aerosols absorb the heat and maintain the heat. And these dust aerosols reflect the radiation back in different directions. So that was known as the aerosol direct effect. And that's meant to illustrate exactly how aerosols directly impact radiation. The key word is direct. Now we'll go over the aerosol indirect effect. So under cloudy conditions, this slide is meant to reflect what we term the aerosol indirect effect, okay? So we have water droplets and we have cloud condensation nuclei. Now, contrary to popular belief, every single cloud that you see in the atmosphere is composed of small particles at the nucleus of every water droplet. And these small particles are in essence aerosols. So yes, aerosols are very, very important to humanity. So let's say we just have this typical cloudy condition, right? Where we have these cumulonimbus clouds over the Gulf of Guinea, right? Encroaching Southwest Africa, typical summer activity, right? or all year activity at least. Let's say, oh my goodness, we introduce some more aerosols into our cumulonimbus clouds that are already precipitating. If you want to know what's going to happen next, right? Well, there's a couple of things that will happen. Well, one, we increase the amount of cloud condensation nuclei within this cloud without actually increasing the cloud itself. So there's actually a few things that can happen. One, the amount of precipitation reduces, right? When you have more cloud condensation nuclei, this tends to decrease the size of the droplets. And when you have smaller water droplets, you tend to have less precipitation efficiency. I'm trying to use the correct terms. And in addition, when you have less precipitation, this will lead to a longer cloud lifetime. So if the cloud's not able to rain out, it's gonna be present for a longer period of time. And this will actually lead to this an increase of radiation being directed back into space, or what we call cloud albedo. So you're probably trying to think, what happened in that last slide? This arrow right here meant to reflect the radiation coming in, being bounced off the top of a cloud and bouncing back into space. It actually increases as we increase the amount of cloud condensation nuclei, because these clouds are lasting longer. And when you have longer lasting clouds, they're able to accumulate more liquid, okay? So that's essentially the aerosol indirect effect right there. And this leads to what we call drizzle suppression and higher albedo. These are very common terms in the aerosol science community, but I know that it's probably not that common here. So I'm dumbing this down. So definitely, if you have any questions later, jot them down and I'm hoping to answer them. Okay, and now there's a less talked about effect called the aerosol semi-direct effect. Me personally, I don't think it gets much love, but it's spoken about less because it's not really well understood. And in order to just rush through the explanation of it, the semi-direct effect is defined as the rapid adjustment within the atmosphere associated with absorbing aerosols, which perturbs the temperature structure and cloud distribution. So if I can just go back a few slides here, and I mentioned that, hey, during the aerosol direct effect, you have surface cooling and atmospheric warming. Think of a temperature profile. Think of the temperature profile before and after aerosols are introduced. Now, after aerosols are introduced, there's going to be an adjustment to the temperature profile, right? Because normally temperature cools as you go higher in altitude. But if you have absorbing aerosols, then essentially you're going to have warming temperatures as you go up in altitude, which can actually lead to cases of atmospheric stability. But maybe I slightly digress. Anyway, we have here the aerosol semi-direct effect. And here for the semi-direct effect, it really matters where the aerosols are located in proximity to the clouds. And here we can see that we have two scenarios. We have a scenario where we have aerosols located within the cloud. And then we have another scenario where aerosols are located above a cloud. And for this exact scenario, I want you all to think of absorbing aerosols. So Dr. Ajoku just inserted some absorbing aerosols within the cloud, let's say on the left side, and absorbing aerosols above a cloud on the right side. And we'd like to know, well, what exactly is going to happen? That's actually a good question. It's still being studied, but there have been some previous studies that helped elucidate, a nice word, that helped elucidate any type of confusion we had on this topic. So we have two things going on. In one case, we'll have a shrinking of the clouds, maybe not that dramatic, but hopefully that caught your attention. So in the case where we had aerosols within the cloud, that tends to lead to what we call cloud burn-off, because we have absorbing aerosols, absorbing heat within the cloud, which can lead to the dissipation of the cloud. And in another case, sorry, that happened too quick, we have a thickening of the cloud, which is happening on the right side. So the temperature adjustment from having these absorbing aerosols above a cloud leads to something called dry air entrainment. And that dry air entrainment can lead to what we call a cloud thickening. So it's very important to understand where these aerosols are located in proximity to the cloud base or the cloud top. All right, so continuing on. So by now, everyone understands aerosols. Near the African region, we understand the different aerosol impacts. Now I'm going to try to introduce exactly how aerosols come into play with precipitation and land cover. Okay, so season after season, year after year, people are setting fire to the African landscape to create and maintain farmland, grazing areas, and things like that. So what you're looking at here on this slide is the transition from the location of fires from predominantly in the Sahel region, starting in boreal winter or in January, towards the southern hemisphere in what we call boreal summer, or leading towards August, September, and into those months. So here what we're looking at is just the transition of fires, of the location of fires as the year progresses on. And what you're going to notice is that, well, the location of the fires are opposite of where the ITCZ is located, right? So the ITCZ, Intertropical Convergence Zone, we all know where that is, but it's important to understand, its movement throughout the year and what that means for fires. So in January, when the ITCZ is shifted further south, right, or closer to the equator, that's where we have more of the fires happening in the Sahel region, right? As you can tell here. So look at January. This is where more of the fires are happening. And here, the ITCZ is shifted further south, whereas the opposite is going on in August. The ITCZ is shifted further north. So as you can expect, we're having fires where we have the least amount of precipitation. And of course, in August, that's going to be in Central Africa, going towards Namibia and Angola. So now we're putting this connection together of, okay, aerosols, aerosols are created from fires. Fires are happening in the opposite of the ITCZ movement. So this led me to creating a research flow chart, and I wanted to answer a few specific questions. Well, one, how do variations in aerosols emitted during the seasonal biomass burning affect seasonal African climate and dynamics? And in order to answer these questions, I have to look at a few different research articles and understand what's already been done, so I'm not reduplicating anything. Sorry. Hearing an echo. Yeah, okay. So when I decided to answer this research question, I noticed that there were answers to this research question on both sides of the spectrum. Some scientists thought that, well, when you increase smoke, you limit the upward convection and this suppresses precipitation. On the other hand, you had some researchers saying that the initial cloud fraction actually determines whether aerosols can suppress or increase precipitation growth. So it's clearly undecided what role aerosols have in aiding or suppressing precipitation. So now what I would like to answer, and what I didn't mention here, is I want to understand exactly how these fires are actually intersecting or interacting with the West African monsoon. And I'm going to go over some research already published on that in a minute. So there have been recent aerosol measurement field campaigns throughout Africa, and it actually pains me to see that none of these field campaigns are actually headed by an African university. Most of the universities that are, in charge of these field campaigns are either from Europe or even the US. So hopefully I'm thinking that something like that can change into the future. But here's just a list of the field campaigns that looked at how aerosols interact with clouds, precipitation, and the West African monsoon as a whole. I'm not going to go through all of them, but just going to leave this here for your personal edification. But you really just want to say that for the last 30 years, maybe even slightly longer than that, there have been numerous amounts of field campaigns to study the interactions between aerosols and precipitation. Because as you can imagine, For us, like our modeling capabilities are not the best, and they're even more worrisome when we try to model Africa because of the scarce, the scarce observations. They're really hard to come by. So just keep that in mind. So now I'm going to go over exactly the results that I found of exactly how aerosols impact precipitation during the West African monsoon season. So not going through everything in full detail, we wanted to understand exactly how aerosols from Central Africa during the peak monsoon season, how they may impact the Southern West Africa. So we decided to look at aerosol composition in the Gulf of Guinea, because the Gulf of Guinea is directly adjacent to Southwest Africa, where most of the precipitation is falling during this time of the year, specifically for the month of August. So one thing we notice is that the intensity of the trade winds over our source region really determines how much stuff is being transmitted towards the Gulf of Guinea, or how much aerosols is being transmitted over here. So we noticed that whenever the trade winds are stronger than normal, we have what we call our dirty days, where our aerosols are more polluted in this region. And we noticed that when trade winds aren't as strong, we have the opposite, or what we call our clean days, when aerosols aren't as polluted over the Gulf of Guinea. And the reason that we're looking at the Gulf of Guinea is because, once again, that's directly adjacent towards Southwest Africa, and aerosols suffer from something called precipitation washout. So if I were to try to create this same composite over Southern West Africa, I really wouldn't get a signal, because on average, there's a large amounts of precipitation occurring over here, and these aerosols would be washed out. So I'm trying to capture the meteorological conditions right before these aerosols make land cover. So now we've deciphered our dirty and our clean days. And next thing we wanted to do is we wanted to look at exactly how are the clouds looking like, and specifically the cloud water radius. So during our dirty conditions, we noticed that the clouds are thicker and the size of the droplets are smaller, right? And we noticed that during our clean days, we have the opposite. Our clouds aren't as thick, they're actually thinner, and our droplets are actually larger. Now, maybe you're probably thinking, that seems familiar. Didn't you talk earlier about droplets and something like that? Well, actually we did here when we talked about the aerosol indirect effect. And clearly what we mentioned here was that when we increase the amount of CCN within a cloud, we have a drizzle suppression and higher cloud albedo, or thicker clouds. And lo and behold, that's actually what we find over here in Southern West Africa during our dirty and our clean days. So to me, this was kind of like, and this is like really important, because we're finding an interhemispheric connection between aerosols emitted from Southern or Central Africa and possible impacts in Southwest Africa, which many people weren't really focusing on. And this actually, we found out that this actually leads to a reduction in precipitation during our what we called our dirty days, when we had more pollution over the Gulf of Guinea. And we actually find an increase in precipitation during our clean days, when we had less pollution over the Gulf of Guinea. Now, this project that I published a couple of years back, this is done with purely observational data. So I'm still walking everyone through how I personally conduct research. And if I were to continue on this research, the next step would be to conduct a modeling study. So there's just one more topic I want to go over real quick before I talk about vegetation feedbacks. So now I wanted to talk to everyone about how aerosols can potentially impact what we call a stratocumulus to cumulus transition, which is basically a cloud transition area over the open Atlantic. We decided to look specifically just for the month of June, and we wanted to answer a couple of research questions. One, can we see a transition region where biomass aerosol emissions impact low-level cloud fraction? And two, what are the important mechanisms of biomass burning aerosols impacting the spatial structure of this transition? But first, we need to ask ourselves exactly how do stratocumulus clouds form, right? So we all know that the Earth spins on its axis, results in the Coriolis force, pushing the ocean surface away from the mid-latitudes. This actually results in upwelling of cold water from below. And when you have upwelling cools the air directly above the activity, right? And when you have upwelling, this results in a temperature inversion. And you have a stabilized atmosphere, which prevents deep convection. So when you have regions of upwelling or locations of massive upwelling, chances are you won't have cumulonimbus activity there, right? And where we see most of these stratocumulus clouds form are where the location of eastern boundary currents. And where we have eastern boundary currents, as you can see here as the locations in blue, everywhere you see it, well, I should say almost everywhere you see an eastern boundary current, you have it transporting cooler waters equatorward. So you have an area of cooler sea surface temperatures. And this happens to coincide with the location of stratocumulus clouds. And if you were to look at it from a purely satellite perspective, you would see that these are areas with a large cloud fraction. So the prevailing theory for this stratocumulus to cumulus cloud transition was proposed by Chris Bretherton in 1992, I believe, and another professor named Wynant in 97. And it says that this stratocumulus to cumulus transition occurs due to the advection of cloud systems over a continuously increasing sea surface temperature. And that's what we're seeing here. So just imagine that we're in the Atlantic Ocean and we're going from, let's say, 20 degrees south towards the Gulf of Guinea. Let's say this is the coastline and this is Port Harcourt, where my family's from. We have a cloud system moving over continuously warming SSTs, right? And that's what's just creating these different cloud regimes and more so this large scale cloud transition that we're seeing, right? So this is what's termed a stratocumulus to cumulus cloud transition. And within this transition, we have a subtropical high, right, to the south, and we have the equatorial low to the north. And this is what's creating a trade wind inversion. So we have this large scale subsidence as a part of the Hadley cell here further south, which keeps these stratocumulus clouds in check, right? And that's kind of like the other piece besides upwelling of what helps stratocumulus clouds maintain their location and their vigor. We have the large scale subsidence from above as well as upwelling from below. So in essence, what we're looking at here, you can say is a sideways view of the Hadley cell. So this is a satellite view of a random date in June 18th. And here I just wanted to illustrate that on this day, we have two distinct cloud types. We have stratocumulus and cumulus cloud types, as well as various aerosols that are present. So anyone can go on NASA's World View, that's what it's called, NASA World View, and you can find data just like this. And so here what we're looking at is stratocumulus and cumulus clouds to the left. And on the top right, we're looking at various aerosol types. And here we can see right between this transition where stratocumulus and cumulus clouds are, we have a layer of smoke. And that's really important for me because I wanted to study exactly how smoke impacts this transition, which I did, and we published that, but I don't want that to be the focus right now. So I'll just leave that part right there. But I really wanted to show this slide because I wanted to show everyone here that you can literally just do research by going on NASA's website and finding your own. This slide that you're seeing here was actually on a paper that I published. And you can definitely ask me more questions about that later. Okay, now I wanted to transition to land cover interactions. So over Central Africa, we have different vegetation types, and that's what this figure shows here. I wanted to focus primarily on grasslands and savanna vegetation types because that's where most of the fires are occurring during the burning season. Whether you're looking at the dry season, over Nigeria, or you're looking at the dry season over Central Africa, most of these fires tend to happen where we have woody savanna as well as grasslands, right? Now, one thing that I wanted to talk about that I'm not going to go into extreme detail is that over Central Africa, the fires are happening in August, right? It's August right now. It may be raining over there in Nigeria, or maybe it's the little break right now, because I know every August it's not raining as much as it is in June and July. So regardless of the fact, 4 months from now is going to be or 3 to 4 months from now is going to be the start of the burning season. Now, I had this weird idea of how, if aerosol can possibly impact precipitation here, can the precipitation impact the fires that's going to happen 4 months later, kind of like a feedback, right? And this work is still in progress, but I do have some neat results that I can show, that's not classified yet. So we decided to look at the trend in various, in different variables over the last 17 to 20 years. And one of them is precipitation. Now, over Southern West Africa, or even Nigeria and some parts of Ghana, over the last 20 years, there's been a reduction in precipitation for the month of August, according to this trend. And actually made sense to me because, not shown here, we have an increase in black carbon and in organic carbon emissions over the Gulf of Guinea during the same time as well. So to me, seeing this decrease in precipitation over Nigeria and Ghana, it's kind of made sense. But what was really more interesting is, if you look further north, we have a very significant increase in precipitation along the Sahel band. Now, this band where my arrow is going across is the 15 degrees north latitude band. So here we can see that we have significant increases in precipitation over the last 20 years. And this hasn't really been talked about a lot, because 20 years before 2000, the only thing that was talked about in the research is a massive Sahel drought, Sahel drought, Sahel drought. But no one's really talking about the fact that it's in a current recovery right now, and the type of implications that can have for the current burn season. So at this point, we notice significant trends. And now we decided to look at the impact changes in precipitation trends have on vegetation cover. I'm pretty sure I worded that wrong, but forgive me for that. So here we're looking at the trend in carbon emissions over Sahel vegetation types for the month of December. And what you can see here is that these emissions have been significantly decreasing through time, right? As our precipitation near this region has been increasing, right? And the reason here I plotted this figure in green is to indicate that there is actually more vegetation, right? Because there's actually more vegetation since the emissions have been going down. Because when you think of an increasing emissions, you think of drier conditions. But when you have wetter conditions, you have less emissions and you have more vegetation, okay? So that's something that I'm noticing right now over the area. I'm gonna publish a paper on that within the next 5 months. Definitely just want to, mention that to everybody. And last but not least, I wanted to just talk about some of the ongoing and future research that I'm doing. One of them being studying something called shared socioeconomic pathways. And that's basically involving future climate modeling studies. So you can run climate models that go into the end of the century. The previous version of this was the A1B, the A1C scenario. And then after that came something called RCP, which stands for Representative Concentration Pathways. And now we're looking at something called shared socioeconomic pathways. So it doesn't matter if you're searching, if you're studying aerosols like me, fires, you can be looking at ocean productivity, you can be looking at anything. And let's say you want to model what's going to happen 100 years from now, right? Now, what scientists do now is that they make these predictions based off of possible scenarios. For example, what if we get our stuff right and we start using green energy, there's going to be less emissions? Or what if we're all just going crazy forever and we keep emitting at the same rate and, the end of the world is coming soon. There's like doomsday scenario and the best case scenario. And you can use these different scenarios to fuel a climate model and try to anticipate or decipher what may happen into the future. So that's exactly what I'm doing here, using these surface carbon emissions, right, over Southern Africa, since I know that they're the source, they're aerosol sources from fires that are being emitted over the Gulf of Guinea. I want to understand exactly how that can change into the future. And when you take into account SSPs, these scenarios also take into account the world population. So this is just an example here of different scenarios in the world, in the population, right? So as you can see here with SSP3, this is more so of a worst case scenario because our population balloons by 2100. And you can make many more inferences from here, but I'm not going to bore you to death with that. So for example, let's say I wanted to use these SSP scenarios to understand how various changes in emissions can impact, something I may be looking at. It doesn't really matter what. So here I can look at the surface of fine mold black carbon fluxes to understand how exactly black carbon emissions may change into the future. And as you can see, there's one worst case scenario where, emissions are higher than normal, but they all have different trajectories. So just want to, keep that in mind. There was another slide I could have shown with this, but these impacts actually, the different trajectories that surface black carbon emissions can take actually impact the amount of precipitation occurring in Southwest Africa. I just didn't include that because, it's more on the classified side. All right, so I talked your ear off enough, I'm sure. I wanted to end this off by saying that I am recruiting students. If any of the mentioned research piques your interest, definitely holler at me, find a way to get in contact with me. I'm looking for master's students, PhDs, as well as postdocs. And there's a possibility that, your education could be fully funded. So I'm talking slow on purpose and I'm leaving my email here in case anybody's writing it down. I realize right now that my computer is dying, so then I'll stop talking. And yeah, if anyone has any questions, please, 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 please entertain me. All right, thank you.
Thank you, Osi. That was an incredible talk. All right, there are plenty of time for questions. And I think someone had a question kind of in the middle and I said to wait until the end. So now is a good time to ask any and all questions that you have. You can either unmute and start speaking, or you can raise your hand. I can get things started while people are coming up with their questions. I was actually curious about the term science diplomat that you mentioned at the beginning. What did you do for that? And what do you mean by that?
I'm glad you asked that. So science diplomacy is a term that I got introduced to relatively, I guess, not that far into the past. So we have something here called the American Association for the Advancement of Science, the AAAS. And what they do is that you can act as an advocate for science on behalf of, let's say, whatever country you want to represent in political affairs. So for here in the US, it would mean being involved in something called the United Nations, going to things such as the Conference of Parties, and doing your research in terms of diplomacy. So let's say, for example, we have SDGs. We know about these. We know about sorry, I'm forgetting the name, but it's the intentionally, I forgot, it's a goal by every country to reduce carbon emissions, but I think it's called the IDG. I'm forgetting. But yeah, so you have an intentionally determined contribution or something like that. So you can help governments using your research figure out ways to abide by these climate mandates that are being put forward. So for example, if your government's trying to go green by 2030, 2050, you can actually be there with real research, figuring out ways of how to get this done. And that's what a science diplomat does. It's not only one hat. I know somebody who works at NASA and is a science diplomat as well. So yeah, I think that's just really interesting. I like to see myself as a science diplomat to Nigeria one day, using my USA resources. But I can hope and dream, right?
Yeah, thank you. I like how yeah, you have some big dreams, and I really hope that you can make them happen. That's really wonderful. Okay, we have some questions. Daniel, go ahead.
Yeah. Hello. Yes. Thank you very much for the presentation. Yes. So I want to ask two quick questions. I want to find out the semi-indirect effect of the aerosols. How is the shrinking of the clouds be measured? So that's the first one. And secondly, I want to find out, so the impacted clouds, irrespective of what the aerosols are doing to the clouds, are the clouds not moving, like I mean to other areas? Because I think from what you discussed, you were talking about the southwest of West Africa, southwest of, yeah, Africa, yes. Yeah, thank you.
Oh man, so these are great questions. And if I'm trying to see if I understood the first one right, you said, how do you measure a cloud shrinking?
Yeah, for the semi-indirect effect of the aerosols, yeah.
I'm glad you asked that, because when I say that initially, most people might be like, how the hell does a cloud shrink, right? So one thing that we've done to like figure that out exactly is that there's been experiments done in the cloud chamber, right? And in the cloud chamber, you're able to simulate a cloud under conditions, right? You can raise the humidity, lower the temperature, increase the moisture content. Voila, we created a cloud. Then you can inject aerosols, right? That's, let's say absorbing aerosols or smoke, and see exactly how this cloud reacts. So in that case, the cloud dissipates, right? So that's what I mean by cloud shrinkage. I put the cloud shrinking to kind of like draw on your attention, but really think of evaporation. That's essentially what's going on. Now, in terms of the second question, you brought another valid point, right? Because essentially what you're talking about is Lagrangian versus Eulerian, right? Is the cloud moving within time, or is it in a fixed space? So the clouds are moving, of course, right? And in a sense, everything is moving and evolving together. So let's say you have an aerosol and a cloud clumped together, but they're moving at the same time. You still want to understand how that cloud would evolve with the aerosols inside or around it, and without the aerosols inside or around it. And that's where we use climate models, right? Because we can only see things in nature and just understand, okay, this is what something is like in this time and space. We measured 70% cloud fraction. We measured, let's say, 12%, biomass, whatever content. You can redo that in the model and slightly change the configurations and see exactly how that may change to infer the impact that these aerosols have on a cloud like that. Hopefully I answered your question without creating more confusion.
Yeah, it's helpful. I've been helpful. Yeah, thank you.
All right, thanks. Uzoma,
Hello.
would you like to go?
Hello.
Yeah, good afternoon. Thank you so much, Osinachi. The presentation was very nice. I recently started getting information as to the importance of these aerosols and dust particles and their impacts on climate and so on and so forth. So I just want to make a comment and then ask a question. You said something earlier on that a lot of campaigns that have been done to study these aerosols within Africa are not carried out by or are not spearheaded by African universities. From the little I know, I found that to study these things need very advanced and most times very customized instruments, right? And it's something we've been saying since the beginning of this session today that access to these instruments and even the funding for even if it's to construct them indigenously, it's something that is very hard to get in Africa. So that is really one of the major drawbacks in that to that respect. But now to ask the question, would you say that um, like via NASA or via how you get your data, would you say it is possible to get sufficient data for, let's say, aerosols and clouds in within Africa right now? Let's say from NASA or from satellites. Would you say it's possible to do that?
Definitely. I would say it's definitely possible. So, and that's the reason, like, I kind of slightly maybe bored y'all, like showing y'all the research, is because the research that I showed were actually public. They're actually in publications. I publicized those research in known journals, and I literally just used observations, right? And I was just, searching the internet, and all the data that I showed, I found through the internet. I didn't need any special access. I didn't need no special ID. I didn't need a secret handshake. They're all openly available. And that's something that, I'm really glad you said that there's not really the instruments to handle that type of research in Africa. And that's why I'm really recruiting, right? Like at Howard University, many people might not know this, but Howard University is a HBCU, historically Black college and university. And I'm trying to create a hub for Nigerians and even like Africans as a whole can come here and learn atmospheric science, can go back home and, do other types of research. We have so many instruments here. Like in terms of instruments, like where I'm at is the instrument hub. But like, I want to create an avenue where people can come in, learn. If you want to stay in America, cool. If you want to go home, still cool. But like, get these real skills. We have so many instruments. But I just need to get students here, right, to build the type of programs that out there to get them the instruments. But like you said, it's tough when you don't actually have the instruments over there. So it seems like you're reliant on Europe or America, for help. And that's where I'm trying to change that. But I'm sure that's a 10, 20-year plan.
Thank you so much. That's very nice to hear. That's very nice to hear. And another thing, when you get your data, what level of will I say computerization or analysis do you need to do? But I guess I know that. But what I'm asking is, let's say, what programming language, what degree of complexity, like what exactly do you have to do before you can say, okay, fine, this is your result, and you come up with something?
That's a good question. I use MATLAB, honestly. I know a little bit of Python, but like to me, MATLAB is my bread and butter. When I first came up in grad school, Python wasn't that popular yet. It was something called IDL, Interactive Data Language, and MATLAB. But essentially, MATLAB and Python are very similar. Yeah, I can talk about coding forever, but I don't want to digress because I feel like that's how my brain works. I think about 1,000 different things. But anyway, but yeah, to answer your question, MATLAB. And I share code, and I don't mind doing any of these things. Ideally, I'm supposed to be there in person, but anyway, that's for another day.
All right. I have a question for you.
Yeah.
And I was about asking about the question this last person asked, and they was asking about how you get to analyze your data. I was about asking what kind of software you use, but when you said MATLAB, it's fine. So for my other question is, what are the long-term effects of the cloud shrinking you talk about? The cloud shrinking you talked about earlier. What are the long-term effects of that on climate change? Is there a large-scale changes that it could cause on our climate? If there is, you could just share a bit with us.
That's a good question. I can't say that there's long-term effects because the things that I study have more of a short-term impact, 3 to 5 day schedule. So if there's a large aerosol outbreak and it's raining heavily during the monsoon season, and this large aerosol outbreak causes a reduction in precipitation, it might just feel like, oh man, we got a small relief. But let's say 30 years is going on and you have an increase in these outbreaks and aerosols, right? Maybe let's say the aerosol emission is increasing through time. And we know that these aerosols are impacting precipitation. It'll show its later on. And maybe in this case, it might be soil moisture. It might be soil moisture for a specific month, right? Maybe, and I'm looking at August and I saw that the increase in precipitation is happening further north. So in terms of like a long-term thing, we would say that there's going to be less emissions, right, for fires, where there's more precipitation happening. Now, let's say it's the opposite. Let's say there's a lot of aerosols keep emitting and this decreases the precipitation. This can exacerbate drought. In a long-term scenario, like through soil moisture. So it's like an indirect feedback. It's not going to directly slap you in the face, if that makes sense. Right. And another thing, right, and one last thing I can say is I don't study dust that much, but something that some people have been doing is they've been studying the phosphorus deposits into the ocean from dust outbreaks over the Sahara Desert, because this dust is going from the Sahara all the way to Barbados, in Central America even. So all along the Atlantic Ocean, you have deposits of phosphorus from these dust outbreaks, and that actually impacts, activity underwater, right? So that has another different effect. So there's so many things, and just, I'm kind of getting excited because there's things that we still don't know about aerosols. So that's what's really cool about it for me.
That was helpful. Thank you. Thank you so much.
Thank you.
Okay. Well, thank you again. This is about time to wrap up. That was a really wonderful session today. Just one amazing talk after another. So thanks for rounding that up for us, OC. So we will be meeting back again tomorrow, and we have, I'll be sending out another email on Slack. Let me stop the recording. We don't need this recorded.